In this video, we'll complete our tour of the LSC model. And as you recall in the previous video, we fitted the CMT curve with a 9-factor LSC model, and we derived this spot rate curve from which we can then use it for valuing all sorts of different instruments, which will be illustrated in several different contexts throughout the remainder of this book. The key at this point is that the error, there is a fitted error. For example, if you look at this observation right here, that the CMT yield, the fitted curve is too high, and then further out on the curve at the 20-year mark, the estimated yield curve is too low. The key thing is that overall these errors cancel each other out because of the least squares fitting methodology. And our interest in the long run is really going to be focused on how the parameters of the fitted curve change over time. And so these estimation errors are not a major concern, because our goal, if we're focused on risk management, is not so much getting the precise valuation, rather we're interested in how the valuation changes. And so let's take a look at how we actually deploy the LSC model with several examples. We'll look at the US swap rates. It provides a very good fit. Sometimes a good fit has a very low R squared, and we'll look at examples of that. We'll look at different slope coefficients and different curvature coefficients to try to understand how this model works. And so this is a spreadsheet representation of fitting the LSC model. The swap rates for 1 year out to 30 year are provided as the Y variable. The X0, the intercept, is not shown, which they would all be ones. And then X1 and X2 are the slope and curvature coefficients as illustrated in the equations given previously. The main thing to observe is, even with the 3-factor model with the scalar set at 2, which is what Steely recommended as well as several others for treasury data, the type of data that you're examining will govern what kind of scalar to use. And what we observe is that the fitted curve fits the swap rate curve extremely well. And this is not that unusual. It's very typical to get an extremely good fit. And so this is an example taken on January 1st, 2002. And what we see is the actual curve and the fitted curve are on top of each other. And so this linear regression is able easily to fit a nonlinear relationship. And figure 9 in January 1st, 2019, what we have is a very flat curve. And if you'll notice, the R square is very low. And so in the previous slide, the R squared was above 0.99, extremely good fit. Well, this fit is also extremely good. The problem is that the squared errors are very small. And so although it appears that this model doesn't fit very well, clearly it does. And so if you see a low R squared, you may want to check your curve just to see if there's very little variability to begin with. And so this is an example. This is fabricated a nearly flat curve, but the R squared is almost 0. And so typically, if curves are very flat, there's you have to be cautious in how you interpret the R squared. To get better acclimated to the LSC model, the level parameter is just always 1, the X sub 0. X sub 1 is the slope parameter, and what you see is the weighting is heaviest as you get closer to maturity, and it is the least as you head towards positive infinity. And so the combination of these two, clearly the slope applies more weight on the front end of the curve, the level applies it consistently across the curve. And so level, slope, and curvature applies more weight roughly about where the scalar is. That's not exactly true, but it's in that neighborhood. And so the heaviest weight is given around the 2-year mark, and then less weight is given on the short end as well as the long end. If I have a 2 curvature model and the scalar for the second curvature is 5, what you observe is the weighting for the curvature 2 applies more weight the further out on the maturity structure. And you could continue to build this out with a variety of different curvatures. And so it's just a matter of where you want to apply the weights. As you use this model, you'll get more comfortable with how to interpret the different parameters. If we focus now just on the 3-factor model, and what we're going to do is we're going to change the scalar from 0.5 to 2 to 5 to 20. And what we'll notice is the weight applied, the curvature emphasis is at the short end. If it's 0.5, the weights of the slope drop off rapidly. When we make the scalar 2.0, the weights on the slope drop off less quickly, and the curvature weight doesn't rise quite as quickly. At the 5-year mark, you notice that we're applying a lot of weight on the front end of the curve. It dissipates much more slowly, and the curvature moves out also. And when we get to the 20-year, we have the same sort of phenomenon with more weight to the front end. And so basically, as you change the scalar, you can assign different weights across the curve. If you're a bank, you may want to assign a heavy amount of weight to the first couple of years. If you're an insurance company, you may want to assign the weight to the longer end of the curve. It's just a matter of what the particular task at hand, where you set the scalar. You can also, which is beyond the scope of this material, you can use a nonlinear model and also solve for the scalar to minimize the least squared errors. Unfortunately, the parameters become very unstable and difficult to manage at that point. And so I'm not in favor of using a nonlinear model. The 3-factor model that with different slopes, if I have a -2 slope, notice that that's actually upward sloping. A -1 slope is not as steep. And so, and then the +2 is the steepest inverted curve. +1 is a little flatter, but not completely flat. A slope of 0 applies a flat line across the curve. And so we can adjust the particular shape of the function by changing the slope parameter. The curvature parameter, if I set the slope to be 0, and if curvature is 0, I get this flat line. If you'll notice with positive curvature, I have this upward sloping bend, and with negative curvature, it's a downward sloping bend. And so the curvature affects how the middle part of the curve behaves. Notice that if I start out with the slope of -2, which indicates an upward sloping curve, again, the curvature coefficients with a -2, it starts out very low and rises more slowly. With a +2, it starts out high and moves up very quickly, and asymptotically gets to the level parameter very quickly. So in summary, the LSC has numerous applications, various yield curves. You can think of Treasury, you could think of some swap rate historically using LIBOR, or the secured overnight financing curve. And there's a variety of different yield curves, say a double B rate or a triple A rate. You can fit credit spreads. You can also fit volatility curves, which I've done some of this with energy. You can focus on first differences. Oftentimes, things like the natural gas curve has a lot of seasonality in it, and therefore it's difficult to actually fit the forward curve of natural gas, but it's not that difficult to fit first differences and then be able to understand the risk you're facing across the maturity structure of natural gas futures contracts. You can also apply this to percentage changes across the forward curve. And what you'll find is I'm going to use this particular model extensively throughout the remainder of this material. I have just found it to be the best in the trade-offs between intuition, goodness of fit, as well as understanding what the trading implications are when your model's running. So in summary, the LSC model is defined and illustrated extensively. It's extendable. That is, you can use a one-factor model, a two-factor model, or as many factors as you want, all the while relying solely on linear regression. My observation with financial data is that it fits the empirical observations very well, and it's widely applicable in a host of different finance applications. In the next video, we'll take a deep dive into the various pieces of R code that illustrate features of the LSC model.